this is Dr. S.P. Arsa from Mechanical and Industrial Department, IIT Roorkee. I am going to deliver my lecture 11 on the subject of strength of material, which is developed under the scheme of National Program on Technological Enhanced Learning. If you just refresh your like the previous lecture, then we discussed many things about the material properties, like if we have the elastic material, the perfectly elastic material, then what exactly the relation is there in between the stress and strain, and that is what you see like we apply the Hooke's law for that, and also we draw the curve in between the stress and strain, like the perfect line was there. And if you are talking about the perfectly plastic material, then you see there wasn't there, like if you have a stone or this kind of structure, then even if we apply the load, there is nothing as such the stress or the strains are there in that kind of material. So we found that there was nothing in like in sort of the stress and strain curve. And also you see, as we discussed about the perfectly plastic material, if the elastic with perfectly plastic material, or if you have the elastic plastic material, means elastoplasto material, which is a pretty common material, then what exactly like the characteristic curve is there in between the stress and strains. So that is what we discussed in the first part of our previous lecture. Then you see we like move to that point where you see if you want to measure the strains, because if we like trying to stretch like stretch one material, then like there is a kind of extension is there in that material, and there are corresponding changes are there in the other parts of material. Then how to set the relation in between you see the extension with the other parts of the contraction. So we were trying to do that part you see in the previous lecture, and then you see like we found that if you want to measure, because you see the strain is a measurable quantity. So if you want to measure the strain in other parts, you see then there are you see like the strain gauges were there, and even you see if you want to measure the strains in the three mutual perpendicular this axes, then we need at least 3 strain gauges. So then how to set those strain gauges to measure the variety of the stresses in the different mutually perpendicular axes? Then you see like we formed the triangle, or we can say like we formed the 3 different mutual perpendicular axes, the strain gauges, that is known as the strain rosette. So you see the 2 types of strain rosette which we discussed in the previous lecture. One was when it is at the 45 degree, then how we can measure, and you see like if it is at the 45 degree, if we set 3 mutual 3 strain rosette at equally 45 degree, then we found that the like the 2 rosette which is at x axis and y axis, the strain gauges, they are simply measuring the normal or the direct strains, while you see the middle one which was exactly at the 45 degree from both of the axes, the y and x, means this diagonal part of in between that, it simply shows like the measuring the strain gauge of the shear strain. So meaning is that you see like if we are keeping all those strain gauges at the mutually perpendicular axes, then we will find that you see all 3 we can simply measure, and we will find that the strains are there, but they are in the different forms of the stresses, like you see the direct strains or the shear strains. So that is what you see we discussed in the previous lecture. And also you see like we discussed that actually if we have the stress is direct stress or normal stress, direct strains or normal strains, then how we can get the principal stresses, principal strains, and where is the maximum stresses are there, where is the maximum strains are there, and they have like a kind of common analog is there. So that is what you see we discussed in that, and also we defined that what is the generalized Hooke's law, means actually what exactly the parameters are there which we can define in the Hooke's law if you see a material is subjected by like the mutually perpendicular normal stresses with the shear stresses. So we found that there are the total 9 components are there, but due to the symmetricity it only like if 6 parameters are there, like you see like we defined that gamma this epsilon 1, epsilon 2, or even we define like with respect to that if we have epsilon x, epsilon y, or this gamma xy, then how we can correlate those things in the form of the Hooke's law. Or you see we define the 2 main elastic constant, one is for within the elastic region, one is for the direct strain component, that is the Young's modulus of elasticity, and one is for the shear strain and the shear stress. So we can set up the relationship in between the stress and strain for all 3 mutually perpendicular directions with the using of either first the modulus of elasticity, that is E, and second is the Poisson ratio, because you see Poisson ratio will give you that actually if you are like pulling this one circular bar, then what exactly the relation is there, that if you are pulling in one bar, then there is an extension and there is a contraction on the other side, then what exactly you can set the relation between those extension and those contractions. So you see, we were trying to do all those kind of the Young's modulus of elasticity for the direct strain and direct stress. But if you are talking about the shear stress and shear strain, then we need shear modulus of rigidity, which will clearly give that actually if we have a shear stress, and due to the shear stress, if there is a distortion in like the total element in x and y direction, then how to compute that? Always you see we need the shear strain, and once we set the relation between the shear stress and shear strain within the elastic region, this shear modulus of elasticity is always an important parameter. So you see, these are all the elastic properties which we defined. So we would like to start from that, and then we will try to set up the relationship between these elastic properties. But also we discussed in the last part of that lecture that if you see this Hooke's law or generalized Hooke's law is valid only when there is, you see, the elastic properties are there. That means you see, if you are working within the elastic region or the elastic limit or proportional limit, I should say, then only these whatever the equations are there or whatever the constants are there, they are working or they are applicable. But you see, in generally the realistic condition says that we need to go with the nonlinear relationship in between the stress and strain. That means you see, this is not the final part where the stress is proportional to strain. If you apply the load and you see if you are going up to the failure part, then there is, you see, there are two regions, one is the elastic region, one is the plastic region. So we need to define both regions separately, and we found that in the elastic region there is a proportionality, but if you go to the plastic region, then there is no proportionality, there is a nonlinear relation is there. So we need to define the nonlinear relation, and in that you see these all elastic constants are not at all valid. So you see here we need to go and we need to analyze all those things, but first our main aim is that what exactly the relations are there in between those elastic constants. So here it is, you see, in this lecture we are gonna start with those coefficients, and then we will analyze all that part. So first, the elastic constant. In considering the elastic behavior of an isotropic material, we also define that, you see, the isotropic material, what it is there, that if a material is showing the property uniform in all the directions, then it is the isotropic material. And anisotropic material, just like wood or any fibers, if they are showing the different characteristics with the different directions. Also we define the homogeneous material, which is, that means you see in the material all points are showing the equal properties. That means you see the directions are not the properties are not same in the all directions, but at individual point the properties are same. So here we are talking about the elastic behavior of an isotropic material, the linear isotropic material, I should say, under normal shear and hydrodynamic loading. We can say that, you see, whatever the elastic properties are there, they are always giving you some sort of constant, and these constants are known as the elastic constant. So we introduce the total 4 elastic constants in the previous lecture. That is, one, the Young's modulus of elasticity, that is E; the shear modulus of elasticity, that is G; bulk modulus of elasticity, that is K; and mu is the Poisson ratio. So it turns out that not all all of those independent these properties are to be there, but they are also dependent on each other. So in fact, you see, we just want to find it out that what exactly the relations are there in between that. So first of all, what the meaning is, that is the Young's modulus of elasticity, which is always coming out from the Hooke's law, that if the stress is proportional to strain, then if you equate those things, then there is a constant, and the constant is known as the Young's modulus of elasticity. So E is nothing but equals to stress by strain. Second is the shear modulus of elasticity, shear modulus of rigidity. So it is coming due to the shear stress and shear strain. So again, you see, we can straightway define for a specific form of the stress, that is the shear stress. So G is nothing but equals to shear stress divided by shear strain. So you see, either E or G both are, you see, working in the elastic region with the stress and strain. Mu is nothing but the Poisson ratio. Poisson ratio always try to correlate the contraction or the extension in the other directions. Like you see here, mu is nothing but minus lateral strain divided by longitudinal strain. Lateral strain is, you see, if we have a just the circular bar, and if we are just pulling towards the x direction, there is a extension in the x direction. So whatever the strain is there in the x direction, that is the longitudinal strain. But whatever the contraction is there in other two mutually perpendicular direction, like you see, in a y direction there is a contraction, in z direction there is a contraction. So this strain in the y or z direction is known as the lateral strain. So if you want to make the relationship between the contraction and the extension, if you are pulling towards the one direction, then you see we can say that mu, which is Poisson ratio, is nothing but equals to minus lateral strain divided by the longitudinal strain. The last coefficient of the elastic constant is the bulk modulus of elasticity, which is nothing but equals to this volumetric stress divided by volumetric strain. Means you see this bulk modulus is always working in the particular volume. That means you see if we have the direct impact of both the mutually perpendicular stresses and the shear stresses, then you see there is a combined effect is there, and due to this combined effect there is a change in the volume, and we can simply compute the change in the volume with the use of bulk modulus of elasticity. So, K is nothing but equals to volumetric strain divided by volumetric strain. So, stress by strain always gives you Young's modulus of elasticity, shear stress divided by shear strain will give you the shear modulus of rigidity, and volumetric strain divided by volumetric strain will give you the bulk modulus of elasticity. So, you see volumetric strain is equal to sum of the linear strain, or we can say the in corresponding XYZ direction, because you see we are trying to capture the deformation in all three direction in mutual direction under the effect of any loading. So, here you see if we just want to define the strain in terms of the volume, we need to go with in corresponding direction XYZ, and we need to compute separately that what exactly the deformations are there, like extension, contraction, whatever it is, and we need to compute and multiply those things to get the exact volume. So, volumetric strain or volumetric stress, we can say that actually whatever the changes are there, we need to concern in the volume domain. Or you see as far as this Young's modulus of elasticity is concerned, only it is based on the axial stress and axial strain. Shear modulus of elasticity is shear modulus of rigidity is concerned, it is simply based on the plane stress, because you see it is simply related to the shear modulus of elasticity. So, shear stress is a direct part is there in that. So, now you see we just want to set the relationship in between those elastic constants. So, you see here first the relation between E, G and mu. E is the Young's modulus of elasticity, G is the shear modulus of rigidity, and mu is the Poisson ratio. Let us just establish a relation among the elastic constant these things and consider a cube. So, again you see we are going for a cube which has a unit width, a unit depth and unit height is there of a material which has a site A subjected to action of shear and complementary shear stresses and producing the strained shape as shown in the figure. So, you see if we are see this figure, we will find that this is a perfect square is there which has equal side on 4. This is A, this is A. So, we can say a unit cube which has a unit length in amongst all 6 faces. So, what is there you see if we are just trying to put under the application of shear. So, you see here this is the shear first part of the shear stress is, because we know that the shear stresses are always parallel to the surfaces. So, you see here these are the parallel forces. So, due to the shear there is a distortion, and distortion is there in the in the angle. So, you see earlier if we have the right angle, that is this, you see if you are talking about this point to this point in this figure. So, this point O and this point, you see this is the initial part, and due to the shear stresses there is a distortion, and then you see this A point which is at the extreme corner of that. So, OA is nothing but now it is my diagonal. So, this diagonal is now shifted. So, this diagonal is now shifted from A to C. So, we have the new diagonal that is OC, and earlier was this is OA. So, now it is nothing but it is a parallelepiped which has you see the distortion right from this. So, we can you see if you see this figure, then you will find that this is nothing but the distortion measurement, and this we can say this is the shear strain. So, we can measure the shear strain and we can get the shear stresses at these points. So, we have both the shear formula, but if you project this thing, means if you put the projection from A to this C line or this OC line, then we get the new point, that is the B point. So, here it is this is the total angle is 90 degree. So, we can resolve these forces on this particular diagram, and we can get that you see if it is at 45 degree or at 90 degree because of the two angle, then what exactly the resolution is there of the forces we can get, or this is you see the gamma which is simply you see showing that the shear strain at these points. So, therefore, a strain on the diagonal, whatever the diagonal OA was there, as I shown you see the OA which has now changed to OC. So, this OA is nothing but equals to change in length divided by original length. So, you see it will give you the strain, because whatever the changes are there in the length due to the shear stresses divided by original length will give you the measurement of the deformation, and this is known as the shear strain. Since the angle between OA and OB is very small, as usually hence OA is almost equal to OB, therefore, BC is the change of the length of the diagonal, which will give you the diagonal OA. So that's what I mean to say, that here if there is a small variation, or there is like the deformation is there, or we can say if the distortion is there due to shear stresses, we can easily compute, and by putting those things we can analyze those like points as it is like that. Thus the strain on diagonal OA, because our matter of concern is OA is simply shifted to some point. So the strain on the diagonal OA will be BC divided by OA, or BC can be resolved by like dropping the diagonal on OC feature. So we have AC cos 45, because the 90 degree was there, so 2 theta was 90, so the angle is the 45 degree. So AC cos 45 will give you the BC. So we can keep here AC cos 45 divided by OA, or we can have the OA like from the triangle, which is equals to A over sin 45, or we can say A into square root of 2. So now if we are keeping those things in the previous formula, then we have the strain is equals to AC divided by A root 2, which has come from OA in the previous figure. So AC over A root 2 into 1 by 2, which is there from the cos 45. So if we resolve these forces, then we have the strain which is equals to A to C. You see that how the distortion is there from A point to C point. So what exactly you see in the shifting is there from A to C. So this is AC divided by 2 times of A. A is, you see, the common side of like the total length of any common side. Now you see, we know that the AC was nothing but equals to like this the distorted part from the extreme corner A to C. AC is nothing but equals to A times gamma from, you see, like if we have the curvature part, then we can simply get this relation. So if AC is equals to A times gamma, gamma is nothing but equals to the shear strain. Like, so we can put those things, you see, like into the previous formula. Then we have the strain on the diagonal is nothing but equals to, we can simply replace the AC by A gamma. So this AC, this A gamma divided by 2A, or we have the strain on the diagonal, which is earlier OA was there and then OC was there. So whatever the change is there, the strain is there, which can be get by like gamma by 2. Gamma is nothing but the total distortion, or we can say the shear strain. So from, you see, the definition, we can say that now we have the strain here. So from the Young's modulus of rigidity, the shear modulus of rigidity is nothing but equals to the shear stress divided by shear strain, or we can, the shear strain is nothing but equal to shear stress divided by this one. Or if we are going for the our condition where the diagonal is stretching and we have the strain on the diagonal, which is the shear strain divided by 2. So we can get the strain on diagonal is nothing but equals to gamma by 2, or it is equals to tau by 2z. So now you see here we have the total strain on the diagonal, which is absolutely dependent on the shear stress divided by, you see, whatever the shear modulus of rigidity. Shear modulus of rigidity is a property of material, that which property is there, if it, whether it is a perfect elastic body or whether it is a this elastic plastic body, or what kind of like the body structure is there. Correspondingly, you see the change of strain is there along the diagonal, or we can straightway compute that, since we are like if we are measuring, if you just try to remind those things, we measure those this Mohr circle for the strain. If the abscissa is the normal strain component on this y axis, we have gamma by 2. So here also, if you want to measure the strain, always it comes as the gamma by 2. So here again, you see, even if you want to measure the strain along the diagonal, we have the similar kind of like the structure, that is gamma by 2, or we can replace by manipulation of the simple formula in the elastic region, which is equals to tau divided by 2z. So this kind of, you see, like relations which we can set up easily for any kind of like the structure is there, and when it is like subjected by a pure shear, because here there is no axial term is there, only shear stresses are being applied and we are getting the shear strain, and then we can set up these relations with the using of shear modulus of rigidity. Now this shear stress system is equivalent or can be replaced by a system of direct stress at 45 degree, because like at 45 degree we are having a similar kind of like the results. If we apply the direct stress at 45 degree, we have the similar kind of planes, the planes are showing the similar kind of nature. So you see, instead of analyzing by shear stresses, we can also put the direct stress at 45 and get the same result. So one set will be like compressive and other one will be tensile. Obviously you see, because one end is going to compress and one end is going to extend. If you see the previous figure, then you will find that one is compression just going towards the compressive side and one is extending towards like A to C. So the all in all, the total effect is like we can observe easily. So both will be equal and like equal in the value to the applied shear strain. So we can simply measure, as you see, the shear strain is nothing but equals to OAB. If I am saying that O is the center point, A and B are the two extreme points. At these you see this is A, this is O, this is B. So we can measure the angle AOB, and if it is distorted, then you see we can simply like AOB minus, if I am saying that the distorted one A dash and B dash, so we can measure the shear strain is nothing but equals to AOB when the straight and when it is distorted minus A dash OB. So whatever the change of the angle is there towards the plane, we can simply measure in the shear strain, and we can say that even if we apply, instead of shear stress, if we apply the mutual like direct stress is mutually perpendicular at 45-degree angle, means if we tilted that part, the similar kind of results are coming in terms of tensile or compressive, and also they will exhibit the equal in value to the applied shear strain. So now you see here the similar kind of like whatever the discussion which we like discussed, the similar kind of things are being shown here in this figure. We have a uniform structure, the shear stresses are being applied at these two corners, and we have the complementary shear stresses just to maintain the balance of this particular element. So we have this complementary shear stresses. So now this element is perfectly balanced under the application of pure shear. So now if I just want to replace those things, what I need to do only just like apply the direct stresses at 45. So here you see these are the like the two main planes are there at the 45-degree angle, and you see here when we have sigma 1 which is positive shear. So sigma 1 is the one norm direct stress, and sigma 2 is the other direct stress, and they are always applied at the 45 degrees. So they can also like exhibit the similar kind of behavior as it is being like exhibited by this behavior on the left side. So you see here sigma 1 is positive tau, sigma 2 is negative tau, and they are exactly at like the 45. So all in all the total angle is 90 degree to each other perpendicular. So thus you see for the direct state of stress system which applies along the diagonal, we can get like the strain at the diagonal, as we discussed in the previous case, that the strain on the diagonal is equals to sigma 1 by E minus mu times of sigma 2 by E, because you see if we apply the load in the one direction, there is an extension. So this extension is created by this sigma 1. So sigma 1 is always is the dominating parameter, so sigma 1 by E, and in other direction there is a contraction, so minus mu times of sigma 2 by E. Or we can say by replacing the sigma 1 and sigma 2 by like the sigma 1 is positive tau and sigma 2 is negative tau. So we can like get the final equation is tau by E minus mu times of minus tau, because sigma 2 is there A by E, or we can say tau by E into 1 plus mu. Or by equating these two like strains, what we can get like, because the strain on the diagonal is nothing but equals to this sigma divided by 2z, because this gamma by 2 was there on the diagonal side AC 8 this O2 A2 O2C, what we had gamma by 2 or sigma by 2z. So if I am replacing this sigma by 2z equal to sigma by like this tau by E into 1 plus mu, what I have like this tau will cancel out, E equals to 2 times of G into 1 plus mu. So now you see we have a relation in between the Young's modulus of elasticity and the shear modulus of rigidity, just you see by equating these two terms, like like these two terms, what we have E by Z is nothing but equals to 2 times 1 plus mu. So you see here we have the direct this Young's modulus of elasticity due to direct shear and this direct stress and direct strain. We have the G which is shear modulus of rigidity, which is due to the shear stress and shear strain. So you see we can simply set up the relation in between direct stress and direct strain component, the elastic component, just if we know the mu, means the Poisson ratio. So we have E equals to 2 times of G into 1 plus mu. By keeping those values we can get the another value. So this is you see like the relation 1. So now you see we have like introduced a total 4 elastic constants like E, G, K and mu, or rather I should say that actually this E, G and mu, it turns out that not all of these are independent to each other, but in fact any of 2, or you see like 2 or 3, they are like can be easily dependent on each other. Like you see in the previous case we found that if we want to calculate E from G, then we should know mu. So you see all 3 are having dependency on each other for calculating. So again you see we just go back to that, we have E equals to like 3, we just want to relate like we have one more relation, E equals to 3k into 1 minus 2 gamma. So by using this k, what we have E over 3 into 1 minus 2 gamma, or I can say that actually if we have gamma is half, means you see this 50% you know like the distortion is there in that, the k is infinite, means if the whatever the distortion, as I told you, gamma is nothing but equals to a o b minus a dash o b dash. So if it is distorted 50%, then the bulk modulus of elasticity is you know like is infinite, or I should say, if I just want to, because the bulk modulus of elasticity is always defining on the basis of volumetric strain and volumetric stress. So this volumetric strain, this epsilon v, which is nothing but equals to 1 minus 2 gamma divided by E into, if we have all three components, epsilon x plus epsilon y plus epsilon z. So you see here, by keeping those things, what we have this you know like E 3 times of sigma by E into 1 minus 2 mu, or I should say you know like if I am comparing those things, then what I have EV equals to 0 if even if the gamma is equals to 0.5. Meaning is pretty simple, that if we have the hydrostate of stress, means if all three you know like in all three directions, if the stresses are uniformly distributed to each other, and if we have epsilon x is equals to epsilon y is equals to epsilon z. So by keeping those things, what I have simply divided by 3. So 1 minus 2 into gamma divided into 3 divided by E is equals to E into sigma by E 1 minus 2 mu, or I should say actually, if I am keeping at this point gamma is half, so half, so 1 it is gone 0. So we have there is no volumetric strain, meaning is that the change in volume divided by the total volume is 0. That means if even if there is, you see you know like the distortion is there due to this kind of in all three directions, but if they are equal to each other, then we can say that there is no the net change, the net summation of the volume, the net change in the volume is 0, or there is no volumetric strain is there in that component. So this is one special condition as far as the volumetric strain is concerned. Irrespective you know like of the stresses, the material is incompressible. Incompressible means even you see, even we are you know like applying the different kind of loading, different stresses are there in the different directions, but even irrespective of those stresses, we have the volumetric strain is 0. That means material is incompressible, or we can say when the mu is 0.5, the value of k is you know like is just going beyond certain things, rather a 0 value of E or volumetric strain is 0. In other words, the material is incompressible. The same meaning is that material is always incompressible, or it is irrespective of the stresses, when you see we have the shear strain is you know like just half of those things, or we can say if whatever the k value is there, that is the infinite at half of the shear strain, as we decide you know like derived in the previous case. So now you see here we have the next relation. So in previous you know like relations, we had two main relations. One, we you know like make the relationship in between the this E into this Young's modulus of elasticity, shear modulus of rigidity, and the Poisson ratio. So we will find that actually you know like E is nothing but equals to 2 times of G into 1 plus mu, and then we found that actually even we can you know like relate E into K, means the Young's modulus of elasticity, to bulk modulus of elasticity, because both are working under the elasticity. So we can relate with the using of even mu also. But in that you see, since it is a volumetric strain, so gamma is also the shear strain is also taking an important place, and if we are keeping shear strain, because it is the total distortion is there, so if we are keeping the shear strain half of the value, then we found that this k is going beyond certain limit. There is no meaning in that, material is highly incompressible. So the net change in volume, the volumetric strain, is giving the 0 value. Here now you see here we just want to make the relationship in between the Young's modulus of elasticity, this bulk modulus of elasticity, and this mu, that is the Poisson ratio. So consider again the same object which we you know like considered in the previous figure, subjected to the 3 equal stresses. So you see here, now we would like to make the relationship between the Young's modulus of elasticity, bulk modulus of elasticity, and Poisson ratio. So again you see we are going to concern the same cubic part in which has you know like all 3 equal all 6 equal sides are there, and also we apply the condition that actually in all 3 directions there are equal stresses are being applied to that. So if we can see this figure, that the sigma 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 is there in all 3 mutually perpendicular directions, and they have the equal magnitude, and you see here these sides A is there. So all 6 sides of this particular cube have the equal dimensions. So the total strain in one direction or along one edge due to the application of the hydrostatic stress, because this is the unique you know like the equal stress or the volumetric stress, this is also given by you know like the sigma by E minus you know like the tau time, because this sigma by E or minus this tau times this sigma by E. So, if you compare all these things, because it is the volumetric strain, or I should say it is the hydrostatic stress, because it has the equal magnitude in all these three directions with the equal sizes. So, we can say that the total volumetric this total strain is nothing but equals to sigma by E into 1 minus 2 times of gamma. So, you see here volumetric strain is nothing but equals to 3 times, because it is the equal. So, 3 times of linear strain. So, we can say the volumetric strain is also equals to epsilon x plus epsilon y plus epsilon z, or we can say that epsilon x is equals to epsilon y is equals to epsilon z if we have the unique features with the uniform stress distribution as well as the uniform sizes. So, we can simply apply those conditions to get the volumetric strain, which is nothing but equals to 3 times of whatever the strain which we got here, the sigma by E into 1 minus 2 times of gamma. So, we have this volumetric strain is equals to 3 times, because it is nothing but the 3 times of linear strain. So, 3 times of sigma by E into 1 minus 2 gamma. So, by the definition of the bulk like modulus of elasticity, we know that it is absolutely based on the volumetric part. In the we are always playing in the volumetric domain. So, the K is nothing but equals to volumetric stress divided by volumetric strain, or we can say this is equals to the sigma by K, whatever the volumetric strain is there, or we can get easily the sigma by K, which is the volumetric strain. So, at one side we have the volumetric strain sigma by K. So, from sigma divided by K we can get the volumetric strain. So, volumetric strain is equals to sigma by K is equals to the first one 3 times of sigma by E into 1 minus 2 gamma. So, if we are equating those things, then the sigma will gone out, whatever you see like the stress component is there. So, what we have at the end, E equals to the Young's modulus of elasticity is equals to 3 times of K, that is the bulk modulus of elasticity, into 1 minus 2 times of gamma, which is the shear stress. So, you see the shear strain. So, we can see here that we can easily relate those like the components, if we know like the exact relationship that actually what kind of material is there, how these stresses are being formed, and what kind of like the strain components are there. And in this case also we discussed that actually if we have the gamma, that is the shear strain is 50%, the half is there, we have the K value is infinite. That means pretty simple, that if we have this kind of thing, then obviously the bulk modulus is infinite, or if the material is highly incompressible. So, that is what you see we discussed about that. Now, we want to like again set up some relationship in between like these elastic constants. So, we have now the 3 new elastic constant, that is the Young's modulus of elasticity E, the shear modulus of rigidity G, and the bulk modulus of elasticity. So, now by just taking the 2 earlier relationship that we have, E equals to 2 times of G into 1 plus mu, and we have E equals to like E equals to 3K into 1 minus mu. So, if I am correlating those things, then we can make the relationship E equals to 9 times of Gk divided by 3K plus G, means you see here the Young's modulus of elasticity can be computed easily if you know the shear modulus of rigidity and if you know the bulk modulus of elasticity by computing this relationship. So, if we have this kind of relationship, now you see again we would like to relate this E and K with the using of gamma as we discussed. So, what we have from the earlier relationship, that modulus of elasticity is nothing but equals to 2 times of shear modulus of rigidity into 1 plus gamma, or we have you see E equals to 3 times of K bulk modulus of elasticity into 1 minus 2 gamma. Gamma is the shear strain. So, now you see if I am like equating both the sides, then what we have 3 times of K into 1 minus 2 gamma is equals to 2 times of G into 1 plus gamma. So, if I just want to relate those things, then we have the gamma, which is the shear strain like is equals to 3K minus 2G, like if I just make the setup of those things divided by 2 times of G plus 3K. So, we have the new shear strain component with the use of this either the bulk modulus of rigidity, or we can say the shear modulus of like the elasticity. So, by computing all those things, we can easily form the new value of the shear strain. So, as we move further, we can get the engineering brief like about the elastic constant. We have already introduced like the total number of 4 elastic constants, that is the Young's modulus of elasticity, the shear modulus of rigidity, the bulk modulus of elasticity, and the Poisson ratio. So, it may seem you see like all of not are independent you see of the others, but they are, you see, if we know the two values, we can get the two other values, or vice versa, you see, you know. But the key feature in that, you will find that the Poisson ratio, because due to the Poisson ratio, or we can say the shear strain, we can get the other three moduluses like Young's modulus, bulk modulus, or the shear modulus. So these are the key main, you know, like the moduluses are there within the elastic region of an object. So now as we move further, we will find that as we defined, if you want to calculate the Young's modulus of elasticity, then we can get easily by, you know, like 3k into 1 minus 2 into shear strain. So if I am keeping those things, we have the bulk modulus of elasticity, that is nothing but equals to Young's modulus of elasticity divided by 1 minus 2 mu, or we can say if I am keeping the value of shear strain as I told you that half, then we have the bulk modulus of elasticity is infinite, or we can say that is nothing but the material is incompressible, and we cannot use, you know, like keep all those you know, like keep all those conditions applicable once we have, you know, like the total is half. Strain, that is epsilon V, is nothing but equals to, because the K is basically based on the volumetric strain divided by the volumetric stresses. So if I am keeping those things here, we will have epsilon V, which is the volumetric strain, is equals to 1 minus 2 times of gamma divided by E into epsilon all. That means, you see, if we have epsilon x, epsilon y, and epsilon z, then the summation of those things. And as I told you that if we have the hydrostatic stresses, that means if all the strains are equal in 3 directions, then we can simply get the 3 times of all, means 3 times of 1 minus 2 gamma divided by E into sigma. So now you see, we can simply replace those features, and if I am keeping the value of half, the K becomes infinite as we discussed, and again you see, you know, like the volumetric strain is 0 in that particular part, or the material is incompressible as we discussed. Further, it may be you know, like again depend on that actually whether the condition is simple tension or simple shear. All the real materials tend to experience the displacement in the direction of the applied forces, and under the hydrostatic loading, means you see, you know, like it is the equal components are there in all three mutual directions, they tend to increase in the volume, and in other words we can say that actually if the elastic constants are there, they cannot, you know, like either E, G or K, they cannot be negative. Meaning is pretty simple, that if any material which is under the state of the hydrostatic loading, always it tend to positive irrespective of whether you see, you know, like the Young's modulus of elasticity is there, shear modulus of rigidity is there, or bulk modulus of elasticity is there. So therefore you see, now based on again the previous relations which we set up, the Young's modulus of elasticity is nothing but equals to 2 times of G into 1 plus mu, mu is the Poisson ratio, and you see E equals to 3 times of K into 1 minus mu. So you know, like if I am keeping those things, then the key feature in both, you know, like in both the formula is the mu value, that is the nothing but you see in the Poisson ratio, which is always you see, you know, like coming from -1, which is equal and less to, you know, like mu which is less than equals to 0.5. In actual practice, no real material has the value of Poisson ratio negative. So this is a key feature is there actually, that we cannot put the mu value as negative, because you see always if you see that if you are, you know, like the mu is always, if you go for the physical significance of the mu Poisson ratio, then you find that it is when you are stretching a material, it is extended in one direction, but in other direction always there is a contraction. So if you want to measure the mu, then always you will find that it is nothing but the lateral strain, means always lateral strain is negative, and we are keeping negative outside. So those negative will give you the positive. So it never be negative, but in the real sense, but as far as the mathematical calculations are concerned, we always use that, okay, now the negative means the contraction is there, the positive means the extension is there. Thus the value of mu, you know, like cannot be greater than 0.5. Again, this is the limiting value. We cannot go in the, you know, like negative side, we cannot go beyond 5, because if beyond 5 is there, then material is incompressible, then there is no compressibility is there in the material, as we shown that actually if you are keeping mu as 0.5, always this K is going infinite, means you see the material is incompressible. So this is the limiting value, mu is always less than 0.5, volumetric strain is negative, which is physically, you know, like unlike just it is unlikely, because when the material is stretched, its volume would be always increase, and when it is increasing, we have a K value which is volumetric strain, volumetric stress divided by volumetric strain is always positive side. So you see, this is the limiting conditions for any Poisson ratio, and if you are calculating in any of the numerical and you found that this mu is going in negative side, or if it is going beyond 0.5, that means there is an inaccuracy in the calculation. So this is, you know, like for the checkpoint to see what the exact relations are there in between E, Z, mu and K. Then you see, if we move further, how to determine the Poisson ratio? Poisson ratio can be determined easily by like simultaneous use of two strain gauges on a test specimen subjected to uniaxial, tensile or compressive. Because you see, if you just go for the physical sense of Poisson ratio, we will find that if there is an like if there is we have a tensile bar and there is an extension is there towards one direction. So, there is one strain gauges which we needed to measure the extension, but there is a contraction is there in the perpendicular direction. So, we need to put the strain gauge in other direction also just to measure that actually how much contraction is there in the other direction. So, like for that at least like we need two strain gauges to measure this extension and the contraction in the respective directions, and once we know the longitudinal strain, once we know the lateral strain, we can simply compute the Poisson ratio, which is equals to minus lateral strain divided by longitudinal strain. So, one you see gauge is mounted parallel to the longitudinal axis just to measure the longitudinal strain as I told you of the specimen, and other one is mounted perpendicular to the any longitudinal axis which will give you the lateral strain. So, mu is minus lateral strain divided by longitudinal strain. So, like that you see here in this figure, it is clearly shown that you see here the first one which is along the length. So, you see here we have this is the specimen, test specimen, and there is an extension is there towards the x direction. So, this extension is due to the tensile pulling. So, tensile pulling is there towards this direction, and along these like we are keeping the strain gauge parallel. This is the electrical strain gauge in which you see like we need to put the center line. So, whatever the changes are there in any of like the distortion, it is simply measured in terms of the change of like the voltage, and this voltage can be measurable. So, what we can do here, this is parallel to this axis. So, this will give you the volumetric strain, and you see the other one just because we just want to measure the lateral strain also. So, we need to keep the other electrical strain gauge just perpendicular to this one. So, you see here we have the another strain gauge which is exactly normal, like you see this is along this one. So, they are keeping in this way, another one is just perpendicular to this upper one. So, this is like that. So, here in this figure it is showing that. So, whatever the contraction is there in the perpendicular direction, that can be easily visible like in this particular slide. So, now we have in one direction we have the longitudinal strain which can be measured by this strain gauge first. In another direction, whatever the contraction is there due to this loading, it can be measured by the second strain gauge. Once you have both the strains, you can simply put in the formula that Poisson ratio is equals to minus this perpendicular means the second one, the lateral strain divided by the first one whatever the readings are there, and this will give you the Poisson ratio at a particular force. But again, the limiting condition in any of the Poisson ratio is that cannot be negative, because always the contraction is there in the perpendicular direction, and we cannot go beyond 0.5, because if we go beyond 5 then the respective bulk modulus of elasticity will be infinite, and once it is going beyond certain limit, then you see if material is incompressible, then there is no meaning to measure any kind of strains part. So, that is what you see we are keeping this mu value in between 0 to 0.5, and mostly you see we are using the mu value, that is the Poisson ratio 0.35 to 0.45. So, this is you see the limiting condition for any of the Poisson ratio. So, these you see like we discussed about many of the elastic constants, like you see mainly based on the 4, that if we have the Young's modulus, if we have the shear modulus, then how to correlate with the using of Poisson ratio. Then if we have the bulk modulus, if we have the shear modulus, then how to relate with the using of shear strain, because you see the shearing part is there, and if we have the Young's modulus of elasticity and bulk modulus of elasticity, then how to relate those things with the using of Poisson ratio. So, you see if you know out of these 4 elastic constants, if you know the 2, then other 2 can be easily computed because they are dependent to each other. So, if you go for independent thing, then you see they are based on the material side, but it cannot be like directly related to other one. If you know the 2 parameters, 2 parameters can be easily founded. So, these you see like all the relations which we set up, and these are the important relations if you want to like calculate all those things together. But the key feature in all those like elastic constants are they are only valid within the elastic regions, because you see like once you go beyond certain limit in the extension, means once you put in the plastic region, all these parameters are invalid, and we cannot put like those relations to calculate the different parameters. So, this is you see this was the one of the key feature was there, and that is why you see all the Hooke's law or all those parameters are applicable within the elastic region if material is applied, and that is why you see like we even define the characteristic curves within the elastic region irrespective of the Young's modulus, shear modulus, bulk modulus, Poisson ratio or other isentropic and homogeneous properties. So this was, you see, like about the key issues of the elastic constant. Now you see we are coming towards the mechanical properties, that what exactly the mechanical property of the materials are there through which we can exhibit the elastic coefficients or the plastic coefficients, and how we can differentiate in between the plastic region and the elastic region of a material. Because you see in the previous lecture I discussed about that if you are talking about the elastic region, that means it is a linear region. And always we are defining that Hooke's law is valid for linear, elastic, isentropic material. So you see these all are the assumptions. So you see if we want to see the clear microstructure of a material, that what exactly is going on when we are applying the load, and you see we are saying that there is an elastic or plastic regions, you see these kind of characteristics only we can analyze once we know the mechanical property of a material. So in the course of operation or any use, all the articles and you see the structures are subjected to the action of external forces, and which creates the stresses that inevitably you see cause the deformation. So whenever you see you apply the load, and as I told you, see the load can be defined by two ways. One is the mass into acceleration, and other one, which is the important property in the stresses, in the point of application of load, that how this load is acting, and due to that you see we can easily find it out whether it is you see towards outward direction, towards the compressive side, or towards you see the shearing, means the parallel forces are there. So what exactly the point of application of this force is. So based on that you see we can easily find it out that what deformations are there within those objects, and to keep those the stresses and the consequently the deformation within the permissible limit, it is necessary to need to select a suitable material for that. Because you see let us say if you are talking about the the RCC rod, and if we keep you see the other material like brittle material like the brass is there, the bronze is there, then it is simply rupture, because it cannot bear out the tensile loading. So we have to be very careful about the choosing of material, that what kind of loading is there and which type of material can bear that kind of loading. So that is what you see this kind of properties is very important to read it out prior to apply the engineering design. Then you see the components of the various designs, and to apply most effective heat treatment, the heat treating is there, annealing, and other these heat treatments are there just to refine the structure. That is the this compressiveness knowledge of the chief characteristic of a semi finished material product and the finished metal articles, such as the strength, ductility, toughness, are really very essential for the kind of engineering design purpose. Because you see if you know the ductility, then we can simply say that yeah, this mild steel is really ductile material, even we can stretch up to this limit, then it will show the elastic limit, elastic region or plastic region, or even we can say that if it is a high speed steel, or if it is a high cut high speed steel or a high chromium steel is there, then what kind of these characteristics they can exhibit under the application of those loads. Or if I am saying that if I am just using the cast iron or this brass or bronze, then what kind of characteristics they are showing and what kind of ductility is there, whether they are showing any ductility property of the brittle material or the simply structure is there, or whether you see they have the what kind of carbon percentage are there, through which we can say that yeah, this much hardness is there and we can apply this kind of loading there. So these either the strength or the ductility or the hardness or the toughness, all these are the key features of any material through which we can say that yeah, if this kind of loading is there, this material is very much suitable for that kind of application. And that is what you see we can even refine through the heat treatment of these materials. So for this reason, the specimen of a material, the metals used in any manufacturing of the various product and the structure are simply based on the result of the mechanical test. So that is what you see what we are doing here prior to apply anything, or if prior to go for any application, we would like to check that actually what exactly the microstructure is there, and if we apply the load like the tensile load or you see the compressive load or the shear stresses or the shear loading, then how this microstructure is changing, and you see whether it can like we are applying up to a certain limit and there is no, and once we release the load, if there is no exact permanent set of change in the microstructure is there, we can say that yeah, this material is very much sustainable or suitable for this kind of loading. So you see prior to go for anything, we need to check it out the microstructure. So mechanical tests are very essential before designing, or we can say that actually the mechanical test conducted on an specially prepared specimen like like the test pieces, always we are first checking on the test pieces only of the standard form and the size on the special machine to be obtained. the strength, ductility and the toughness characteristic of a material. So, you see here these 3-4 properties are very essential prior to go for design of any the object, and we need to check it out that actually whether this can be like sustainable for impact loading, direct loading, shear loading or what. So, you see here this kind of these properties are very essential, and for that the condition under which these mechanical tests are conducted, we are simply categorizing the 3 types. One, the static type, because you see as we know that if the static loads are there, then how these microstructures are changing. So, when the load is increasing slowly, or we can say the gradually, the metal is loaded by tension, compression or torsion or the bending. That means you see here if there is a hydraulic press is there, you see as we can see in our universal testing machine, the hydraulic always loading is always kind of slowly, there is no direct impact is there. So, the microstructure is changing slowly, and as and when you see it is extended, these all elastic limit, proportional limit, yield limit or this plastic limit can be easily clearly defined the what is the limit is there for these reasons, and we can say that actually if you want to show these things on the graph, it can be clearly shown by the graph also. So, this is as far as the static is concerned, because you see the element is under equilibrium when the static loads are there, whatever the forces are there, these forces are simply applying on the outer side, and internal intensity of the resistances are exactly equal and opposite, so that we can say that there is no the randomness or the turbulence is there within the microstructure in the static loading. Second part, as per its name, the dynamic, when the load increases rapidly, because in the dynamic we are saying that the force is absolutely dependent on the time. So, when the dynamic forces are there, just like you see when a shaft is moving, or we can say the gears are just rotating in that, or the camshaft is moving, the impact loading is always coming. So, the impact means actually the high amplitude of load is coming, just boom like that and then just releasing. So, whatever this kind of loadings are there, we have to be very careful, and for designing this kind of the components, always we are taking the dynamic factor of safety, that means higher factor of safety, because it can go up to any extension in the stress level or the strain, and that you see it is very random part is there, and I should say it is momentary, and due to in this moment whether the metal can sustain or not, that has to be carefully designed. Then you see the third kind of loading is very essential, and you can find in many of the machines this third loading, that is the repeated or the fatigue loading, which is very dangerous. So, both static and dynamic this impact type or dynamic types are different, but that is you see when the load repeatedly varies in the course of the test, either in the value or in the nature, value and the direction both, then you see we can say that this is a kind of the fatigue, means the sinusoidal part is there, it is coming in the positive as well as the negative direction, and repeatedly it will come up to certain limit. So, you see here if we want to design the component for this kind of loading, then we have to be very careful in the choosing of the engineering factor of safety, because you see once we choose any kind of factor of safety, yeah, for impact loading that is okay, because the toughness will give you that kind of thing, or we can say the static is there, we can say that the hardness will give you the clear picture. But as far as the repeatedly or the fatigue loading is there, then we have to be very careful in choosing the engineering factor of safety, because all the time you see the microns or the microstructure of the material is sometimes compressing, sometimes extension, sometimes compression, sometimes extension. So, that means you see they are keep on changing, the dynamic forces are there, as well as some part you see they are also facing the static forces, means you see the transient phases are there in between the structure of the microstructure of the element. So, you see here if you want to set up the stresses and the strains within that particular material, you have to be very careful, and that is why you see we have chosen the maximum engineering factor of safety for this kind of loading. And now you see we just want to see that actually that what will happen in the uniaxial tensile test. So, you see in the next chapter we are going to discuss about that what will happen if there is a uniaxial test is there, if there is the combined testing is there, and the uniaxial tension test, always the universal testing machine UTM is very applicable, in which we can apply the tensile test, we can apply the compression test, even we can apply the bending, or we can simply shifting, just applying the torque at the end, we can simply say that the torsional or the shearing part is there. So, you see here in this particular chapter we have discussed about the elastic constant of the various kind, mostly we will find that the 3 elastic constant with the other constraints are there, like you see the E, G and K with the mu and gamma. And also after that you see we simply set up some relations amongst these, and the last part actually we discussed about what the mechanical properties of the materials are and what the importance of these things. So all the discussion is simply based on why actually we are like going for the microstructure as well as the associated mechanical properties are. So in the next lecture we are going to discuss about that if we apply the tensile loading on a uniformly like structured bar, then what will happen if we apply the load and keep on increasing in the static way even, then how we can simply segregate it, the elastic region, the transient region. When you see this elastic region is going to the plastic region, so even there is a transient region, and how we can define the values, the limiting values for these regions, that is also equally important. And then you see what is the plastic region and what are the stress components are there in the plastic region and the elastic region. And then you see generally we are defining the yield limit of that. So what is that yield limit, what will be the proportional limit. So these are some of the limits, and these are you see like the values through which we can say that the material is like simply showing the elastic behavior, and all those constant which we have shown in the previous chapters or in this chapter also can be valid throughout this particular behavior of the material. Thank you.